Yeah, perfect.
Sorry for this. Thank you, Tommy, for introduction. Hello, good afternoon, everybody. I'm going to tell you about using of fan-shaped beams for GISANS. Or more specifically, I'm going to talk to you about our GISANS activity on superradom reflectometer at ILL. And let me start with a brief introduction of the brief description of the instrument. This is monochromatic instrument, which main features are listed here. We have focusing HPG monochromator with very narrow delta lambda. We have variable resolution. We have very high polarization. And we have also very flexible construction. We can change sample detector distance, and we have 2D area detector from Denix. And we have also low background, what makes superradom especially good for high resolution polarized neutron reflectometry, as shown here on this example, and for polarized specular scattering as shown on this example. Now, when I talk about model design of the instrument, I mean that we can not only change sample detector distance, but we can also change sample monochromator distance. We can change position of the slits, beam stops, and basically we can build whatever we want out of our modelers. So now let's see how the beam is formed on superradom. If you look in horizontal plane, it looks like this. This is our HPG monochromators, and we have guard slit. We have double bond periscopic wavelength filter that can be used also as a polarizer if needed. And we have two main collimating slits with variable distance between them. Then we have our sample, which is vertical, and we have horizontal reflection from it. And this is an example of the slit from JJ. Now, if you look in vertical plane, where we focus in the beam, you see now 7 crystals, HPG crystals. Each one is motorized. So we can send, we can use entire height of the neutron guide, which is 150 millimeter, to condense neutrons at the sample position in the beam, which is usually about 20 millimeter. And if you put a pinhole at the sample position and your focusing is properly done, then you see such image in the detector. You can see all 7 crystals. And horizontally, you have this modulation due to the internal structure of the detector. Basically, we see every individual wire instead of detecting volume. So if we plot it in 3D, you see this is our everyday reflectometry experiment, looking like this. Sample is vertical, QZ is horizontal, and along QZ we have typically very high resolution of this value on average, and along QY we have almost no resolution, but we don't care about this resolution because we integrate this picture for the analysis of the reflectometry data. Now the question is, can we use our setup for GISANS? Now, first naive idea would be to slit down our focus beam also in vertical direction to get a kind of pencil-like collimation. And we can do it, of course. And then we see on the detector something like this. This is a direct beam. This is reflected beam, reflected from some sample, I don't remember. It might look kind of okay, but if we take integral, if we take a slice along QY direction now, so we see immediately that collimation is not good enough, intensity is very low, and moreover, all this line is modulated by the internal structure of the detector, making this picture absolutely ugly. We can conclude this approach doesn't work on superradar and will never work for several reasons. So what is an alternative? Instead of playing with the beam, we can try to play with a sample. And the game is very simple. You just turn it 90 degrees and put it exactly in the same beam which was used here for the reflectometry. Obviously, we swap QZ and QY direction. Now we have good resolution along QY, and we have very relaxed collimation along QZ, meaning that angle of incidence is not well defined. Of course, there is no in-depth sensitivity, and we understand all this. Now we want to see, is it really a big problem? So to proceed, I show here one of GISANS patterns. I obtained a lot of them at the synchrotron when I was studying ordering of magnetic nanoparticles at the liquid surface. And this is very typical 2D example of GISANS data containing a standard set of the features, let's say. You have these bragg rods along QZ, which are modulated by the circular intensity or minima and maxima coming from the particle form factor. Then you have horizon line, and you have this Ioneda enhancement line. And basically, in most of the systems corresponding to a monolayer, you always see something like this. Of course, one can analyze 2D patterns, but for our particular purpose, it was not needed. It was sufficient to analyze an intensity along this cut that was presented during this conference several times already. Or in principle, one could integrate along QZ. And then in the end, we have this 1D intensity distribution. And the treatment consists of indexing the bragg peaks, calculating of corresponding bragg positions, comparing to the experiment. By tuning lattice constant, you get best fit between experiment and calculation. And in the end, you have one number coming from this beautiful pattern. So let's go back to neutrons. Once users send me an object, which you can see here, they naively wanted to get reflectivity data from it. But since it was bent, rough, and homogeneous, round with a stupid frame around, reflectivity, there was no chance. On the other hand, the object itself is very interesting because inside there is a porous aluminum oxide film where pores were filled with iron. And all this stuff was kept with germanium layer to prevent oxidation, which makes this system not accessible for any kind of microscopy and by X-ray scattering, by the way. So, but what about GISANS? Having no other alternative, we put this sample in geometry I showed before. And this is 2D pattern we obtained from the object, where in the middle you see direct beam and specular beam sitting together here and absorbed partially by the beam stop. And from both sides of which you have some diffraction stripes corresponding to the lateral structure, lateral periodicity inside of the film, of course. What is interesting, you can see modulations of intensity in these diffracted stripes with the origin, well, what can be explained that sample works as a pinhole I presented before. And you see internal structure of our monochromaty in those diffracted intensities stripes. And again, you see, unfortunately, this internal structure of the detector. If we integrate all this pattern, along QZ, we have such curve, and we compare it with the synchrotron data, which was nothing to do with this sample, of course, but in principle, you see it's more or less the same. In both cases, we can get lattice constant value for both samples. Please note the difference in the Q parallel scale. This one for neutrons, it's 10 times smaller. So we are studying 100 nanometer objects with neutrons, while it was 10 nanometer objects with X-rays. And nevertheless, we still have enough resolution to resolve these breakpoints. So, of course, we perfectly understand that this is not classical GISANS, and therefore we call this one-dimensional GISANS or pseudo-GISANS, or more shortly, GISANS. And the later name reflects in a little bit humoristic way our understanding of the limitations of the method. Nevertheless, it works, and we can do some interesting things with it. So this is the same pattern obtained with optimized setup, and you see break peaks in linear scale, and this is a signal collected in a little bit more than half an hour on Superradom. Another example was done in collaboration with Nicole and Marite from Malmö, who are studying silica particles on silica surface. And they brought several samples, and we did GISANS, a solid air interface. And depending on the particle size, you see different heatings, given full sense according to the particle size. But I'm not talking about science today, I'm talking about technical things. So what is more interesting in this geometry, that nothing prevents us from replacing this solid substrate with a liquid one, which enables GISANS measurements, GISANS measurements at the air-liquid interface, which is not trivial. I would like to outline that all these games doesn't cost us anything. We can just turn the sample and we have immediately this geometry. And for liquid surface, we need very simple equipment like a primitive trough with D2O, and we need anti-vibration device. And of course, we need samples. Thank Nicole who sent me particles, surfactants, and instructions how to prepare such kind of sample in the trough. That was a remote experiment. Could not come, unfortunately, because of COVID. But surprisingly enough, I managed to build this, my first in life, first ever soft matter sample. And this is the data from the sample. Again, you see direct beam, specular beam. For some reason, now we can see also any enhancement of the scattering, and we have the break rods. Again, after integration and subtraction of background, we get, to our knowledge, this is one of the first, and maybe the very first GISANS meaningful pattern obtained at liquid interface. So this study was published last year, and now we are looking for the further technical improvements, developments, new experiments. And in the end, I would like to acknowledge my colleagues again, and our Superradom team in Grenoble, our support Björn and Gunnar in Uppsala, and also our partners Jens in Linköping and Tom in Lund. Thank you for listening.